All right, in order to prepare ourselves for a little more complicated examples, we are going to do a quick lecture on elementary representation theory. And whenever you see the word elementary, what you basically are facing yourself with is a bunch of definitions. And ultimately, that's the truly elementary stuff, right? It's just understanding what the words mean. And that actually goes a long way, because if you understand the definitions of things, if you understand, that really is a way of saying, how is representation theory organized? What are the objects that we want to study? And so if we start with a long list of definitions of things, at least you understand what the theory's about. And then if we can get at some elementary ideas of the theory, some elementary relationships between the objects we define, then we start learning some actual stuff. But this is sort of the way we're going to begin. We're just going to go with a bunch of definitions. You'll see, though, that the definitions already depend on things you've learned. So it's not; these aren't empty definitions by any means. But that is where we're going to start. So you remember way back when we began this thing, we said, all right, we're going to create an object that's called a Lie group, and it's going to be G. And G had to act on a vector space, meaning each element of the Lie group, each element here of this Lie group was a transformation on this vector space. So that if I had an element G and a vector little v, I could create G little v and I'd get W, and W would also be in V. And this was a Lie group of transformations. And that's sort of where we began all of our work. And those are the Lie groups that we're considering. We're considering things that are Lie groups of transformations. There are Lie groups out there that are not this, but we're focusing on the classical groups, right? Which can usually, if not always, be considered as a Lie group of transformations. Now, when you study representation theory, sometimes you throw in something in between here, right? And it's a bit confusing, but the truth of the matter is that if you approach the study from vector spaces, you learn that there is another space associated with a vector space out there called the general linear group on the vector space. And we've already seen the idea of the general linear group, but this is literally the group of all transformations that operate on V, right? So the general linear group is all the linear transformations that could exist on V. And it's a group by composition, right? So if I have a transformation G and a G1 and a transformation G2, I know that G, say 2 acting after G1, right, that's going to be a single transformation G3, which is also in the group. And it'll be associative, and there'll be the identity transformation, and every transformation will be invertible, right? Every transformation is invertible, otherwise it wouldn't be a group, right? So every transformation has to be invertible, and that's where we get this notion of that becomes the general linear group. So if we have this creature, and we have this Lie group of transformations, well, there's often in the literature the step where we go from here to here first, right? We're actually saying, no, the Lie group is something far more abstract out there. But the good news is there's always a one-to-one onto mapping from G into the general linear group which is of all the transformations on this vector space. So a lot of the literature throws this in there. And when it does, that's when you're starting to see stuff about representation theory. Now, when this happens, this doesn't necessarily have to be on two, right? Usually, though, we like it to be one-to-one. And when it's one-to-one and it's a homomorphism, right, then we call it faithful. Meaning that this thing is a homomorphism, right? Because G doesn't necessarily have to cover all of GL. But it's one-to-one. So basically it means the representation of G lies inside the general linear group, right? G is usually going to be something much more restrictive than the full general linear group. But every element of G has one element in the general linear group, and those elements form a subgroup of the general linear group. So that'll be 1-to-1, and such a representation is called faithful. So when you're out there reading the literature on this stuff, you'll find the action of G, right, on V is written two different ways. If G is an element of the underlying Lie group, you might just skip the whole thing and you would say the action of an element of group G on V is G acting on V. If you in fact include this step in here, you're going to do it two steps. You're going to say, well, pi G is the object that's capable of acting on the vector space. So it's pi G that acts on V, right? And these two things should both produce another element of the vector space V, and it should indeed be the same element. All right, now let's consider our group G and our group GL on V, right? And our vector space V, which is, by the way, a group under addition, right? So everything's kind of a group in its own way. So now G, I'm going to redraw G to make it look a little bit smaller to make this point, right? G is a little bit smaller, so G is mapped into the general linear group, right? And we're going to say this map is 1-to-1, and it's a homomorphism, not a homeomorphism, just a homomorphism. That's a group homomorphism. So if it's 1-to-1 and it's a group homomorphism, think about that, right? That means it's mapping to a subset of the general linear group, and that subset of the general linear group is isomorphic to G, right? So this subset here, right, this subset here is actually 1-to-1 and onto G, and it is isomorphic. So the homomorphism is into the general linear group itself, but this particular subgroup, it's isomorphic. Now, that doesn't have to be the case all the time, right? You don't always, your homomorphisms are generally, well, at least when we studied it in elementary group theory, meaning at least when I studied it in elementary group theory, homomorphisms weren't 1-to-1, right? It's this 1-to-1 characteristic. It's this injective characteristic. It's this injectiveness that is so interesting here. And so there's a word for this, is kind of what I'm getting to. The word is, it's a monomorphism. Right? When you have a 1-to-1 homomorphism into essentially a larger group, right? The fact that it's a larger group is represented by the fact that it's a homomorphism. If you had a 1-to-1 mapping into a group that was the same size, it would be an isomorphism. But it's a homomorphism into a larger group that's 1-to-1. We call that a monomorphism, And monomorphisms are typically described in the literature as, well, ultimately we'll talk about why they're representations, but they're called faithful. Actually, I kind of buried the lead here, right? This guy right here, right? That guy right there, that is a representation. That is a representation. This mapping from the Lie group into the general linear group acting on a vector space V is called a representation. All right, so the next concept we want to define, we want to go back up to this guy right here, and let's look at V for a second. So now, V is a vector space, and inside V, there may be a subset of vectors in V. And it may be the case that if I take one of the elements, I'll make it a red element here, I'll call it little v in red. It may be the case that any group element G, right, any group element G acting on, well, the way I'm saying acting in this case is just by putting them next to each other. Acting on V, this is using the, well, I should stick with the notation we're we've kind of started here, right? Any group element G, I convert into the general linear group element that can now act on any element of the vector space V, which in this case will be one of these special little elements inside this little subset that I'm going to define in a moment. And if I do that, and the ultimate result is another element inside that little space, right? No matter what G I choose, right? Every Lie group representation, every representative element of the Lie group, I guess I'll try to be really technical here. Every element of the Lie group has a representative inside the general linear group that lives inside this subset, right? And that representative is a linear action on the elements of this vector space, which means it takes elements of this vector space and returns different elements. And that's what this is. So this is an element of the general linear group, right? And it is acting on a vector in V, and it returns a vector W that's always in the same subspace, no matter what element of G I choose. So I could take any element of G, find its representative, and if I act on an element inside this little subspace, then I get another element inside that little subspace. Okay, if that's the case, if I can find a subspace like that, it's got a name. It's called an invariant subspace essentially of G. It's a property of the group, really, not a property of the vector space. Vector spaces have very little properties, right? Until you give them an inner product. But even when you give them an inner product, they're very simple structures. But so the invariant subspace is clearly a quality of the Lie group, really. But actually, it's not even necessarily a quality of the Lie group as much as it's really a quality of the representation, right? This representation is the thing that's actually acting. And I might have a variety of representations. In fact, that's sort of the point of the representation theory, is to find all the representations of G. Now, they'll all land in here, right? They will all necessarily land in the general linear group on V. But there could be lots of different ways and lots of different pieces of GLV that I could use to do this. And finding all of them is really the idea of representation theory, studying all the different ways that a given Lie group can be mapped into the general linear group. So once I find such a representation, right? Once I find such a representation, that representation will have an invariant subspace of some sort, right? And there are always two invariant subspace, right? The first is we have to remember that every vector space has a zero element, right? So clearly any representation of any group element acting on the zero element will always give you the zero element. There's no linear transformation of a vector space that takes a zero element and doesn't give you a zero element. It wouldn't be linear if that was the case. So that's good. So obviously there's this trivial invariant subspace. And of course, there's another trivial invariant subspace, so that's the zero element. I'll just put that right there, circle it. And the other trivial invariant subspace is the whole group, is the whole vector space itself, right? You know, the whole vector space clearly is always going to be an invariant subspace. So the question always is there another invariant subspace for a certain representation, right? And that's a good question. That's an important part of representation theory, is we want to discover the invariant subspaces of different representations, right? That's an open question. But remember, this is elementary representation theory, so all we care about are the definitions right now. And one definition of an invariant subspace, as we've described, there is a word for the circumstance when you have a representation where there's only two invariant subspaces, the zero element and the set itself, right? And if you have a representation where the only two invariant subspaces are the zero element and the entire vector space, that is called an irreducible representation. Irreducible representation. You guys probably think I'm crazy because I mix these capitals with these lowercase letters sometimes. Like, look, that T and those two R's. I have no explanation for that. Okay, so irreducible representations only have the trivial invariant subspaces. Now, for our work as we proceed, because we're doing Lie groups for really applications in physics, it turns out that a study of all the irreducible representations of a Lie group, right? All these mappings into the general linear group, which are irreducible, that is a pretty complete piece of work. It doesn't cover all Lie groups that are out there. In other words, studying all the irreducible representations of a certain class of Lie groups, namely compact and semi-simple Lie groups. We've already discussed what compact is. I don't think we discussed semi-simplicity yet, but all compact Lie groups that have a property called semi-simplicity, it turns out that all of the finite dimensional representations, finite dimensional means that this vector space has a finite dimensionality, right? Vector spaces can have infinite dimensionality, become a little more complicated and interesting objects that permeate quantum mechanics, for example. Quantum mechanics are always dealing with infinite dimensional vector spaces. But we don't need to always deal with infinite dimensional vector spaces, even in quantum mechanics. So, but for a certain class of Lie groups, studying all the irreducible representations is a very, very thorough analysis of all of those particular kinds of Lie groups. And we're going to work on that as our lectures continue. Okay, so now we're going to consider our Lie group G. But now we're going to consider two vector spaces, V1 and V2. These are different vector spaces, right? Each vector space has its own general linear group, right? And those general linear group are of course, linear transformations that act on V2. So now, G can get a representation up here, which I'll call pi1, and a representation down here, which is pi2. Those are two different representations of the group G, which presumably, well, not even presumably, this is literally defined as transformations on V1, and this is literally defined as transformations on V2. So pi, whoops, I got to make it straight, right? Pi1 of an element G would act on an element V, whoops, would act on an element V to give an element W, where V and W are members of V1, and pi2 of a group element G would act on an element, say alpha, to give an element beta, where alpha and beta are elements of V2. I just went with the Greek letters and the V to distinguish. So, like, I need some way of identifying that vectors are elements of V1 as opposed to vectors which are elements of V2. You know, what I probably could have done is I probably could have just used the same letters but changed colors, right? I could have said, okay, this is V2, which is red, and then I could have gone V and W. I should take advantage of colors, because you can't do that in textbooks, but we can do that on the board, right? It's just if you're taking notes in pen, you can't, unless you switch pens, you can't really take advantage of that, right? So this would be V and W and V2. That's a way of doing it, I suppose. All right, now let me take this. I'm going to shrink it up over here. And we're going to talk about the direct sum of V1 and V2, right? So the direct sum of V1 and V2 is another vector space, which is called V1. Usually it's given like this, V2. Sometimes the circle's omitted. But it's a new vector space, and that vector space is a set. Remember, vector spaces are sets, right? So this is a set of elements and this is a set of elements. So this guy, it's a vector space also called the direct sum vector space. So it's a vector space, so it's got to be a set of elements. It's got to have an addition property. It's got to have inverses under addition. It's got to have a zero. It's got to be commutative under the addition. It's got to be linear with a scalar, all of that stuff, right? So what is it, right? What is the set of things that make V1, V2? So I'll write this here, right? V1, V2. Those are the set of all ordered pairs where the first element, V, comes from V1, and the second element, let's do this in red. Let's see how far I can go with this color thing. The second element, V, comes from V2, right? And that is, so the set of all those elements, right? The set of all these elements is the set that composes V1 plus V2. And how do we add elements together? Well, so actually, I don't want to change colors. That's kind of a hassle, right? So let me just do the Greek letter alpha, right? So V alpha plus W beta, right? Where plus is the operation of plus in this vector space, right? The vector addition property in this direct sum space, that's defined simply as V plus W alpha plus beta, where this plus is obviously from V1 and this plus is obviously from V2, right? Sometimes you'll see books actually make that explicit when they feel like it's necessary. So they would write something like this. They would go V plus, and then they would like 1 W and V and alpha plus 2 beta, where they define a symbol plus sub 1 and plus sub 2, so you know that it comes from this vector space or that vector space. Actually, they would probably name the vector space. So now I have subscripted subscripts, which is kind of a mess. But anyway, the real easy way to track it, of course, is you're always dealing with the addition associated with what's on the left and the right, right? I mean, this is obviously, these V and W are elements of V1, so that addition must be that addition. And these are elements of V2, so that addition must be that addition. And this are elements of the direct sum space, so this must be some kind of addition in this space. And this is how we define the addition in the direct sum space. This is going to be important when we do our more sophisticated example of how to find all the Lie groups for a given Lie algebra. Okay, but why are we doing this, right? So once we've done this, let me erase this. So I'm going to write these two little arrows here connecting these two together into this space, right? Now, there certainly is a mapping, right? These arrows, when you draw arrows between objects mathematically, you're talking about mappings. So you'll notice that I resisted the temptation to draw an arrow here, right? Because you're never really mapping elements of the general linear group V1 onto V1. You're operating, right? So if I drew an arrow, that would be inconsistent with what my arrows are supposed to mean, right? Here the arrows mean a mapping from this group into this group, right? In particular, these are two homomorphisms, right? They don't have to, by the way, be faithful, right? They don't have to be monomorphisms. I kind of went on and on about homomorphism, injective, monomorphism. These don't have to be faithful. If they are monomorphisms, they are faithful, but they don't have to be, right? But if you have these homomorphisms, they do have to be homomorphisms, but they don't have to be monomorphisms. So you have these two representations in these two different general linear groups associated with these two different vector spaces. And then there's this vector space out there, V1, V2. There is a mapping from V2 into V1 plus V2, and it's namely, it would be, if I have an element here in V2, well, I guess I'm using, say, an element alpha, it would map to maybe the unit or the zero of V1, for example, alpha, that ordered pair, right? If this mapping, I guess it would be alpha goes to 0 alpha, that's a mapping from V, that's a mapping from V2 to V1 plus V2. And it's 1-to-1, by the way, but it's not on 2, obviously, right? Okay, so the point is there are these mappings, so I feel okay drawing arrows in that case. The point of all this is that I can find another representation. I guess I'll call it, what do I call it? I guess I have to call it GL V1 direct sum V2, right? The general linear group on the vector space V1 direct sum V2. And I guess it's a group, so I'll put it in a little box. And there is a mapping from G onto that, right? And I'll call it just pi. And that mapping, I can create pi if I know pi 2 and pi 1, or a pi 2 and pi 1. Because remember, there's not only just necessarily one, right? Right? It could, there's like I said before, there's many different representations of G into the general linear group V1 that acts on V1. And there's many different representations on the general linear group V2. So there'll be one, but if I know one, and if I know one of each, right, then I can find a mapping into this direct sum group. And that mapping will be defined the following way, right? It's the pi acting on an element in G, right? Which is a way of saying I take an element of G and I'm looking for an element in the general linear group, right? And that element is selected by this representation pi. So that's what this is. So this guy here is understood to be an element of the general linear group V1 direct sum V2, right? That guy acting on an element of V1, V2, which I'll just write as V alpha, right? This is an element of V1 direct sum V2, right? I've got to get another element of V1 direct sum V2, and I do it in the obvious way. I take pi 1 of G on V and pi 2 of G on alpha. And that guy is also an element of V1, V2. So that's how I define the direct sum of two representations. So that's what this is. This is the direct sum of this representation and that representation. So the way I've written it here is pi, the representation pi, which is into the general linear group of V1 plus V2, is called the direct sum of these two representations. And this is how it's defined, right? This is how it's defined. This is a little bit weird, right? Because pi itself, this is actually a vector space, but we're not defining it quite the same way as you would a normal vector space. But pi is a representation that is the direct sum representation of these two representations. And the reason this is important is that because when we are dealing with groups, the kind of group we've been talking a lot about, compact Lie groups. Remember, compactness we talked about was, you move along in the Lie algebra and the Lie group elements just keep repeating themselves, right? So if you have a compact Lie group, it turns out that every finite dimensional representation, meaning you go into these vector spaces and each vector space may have a different dimensionality. So you will have a representation into a vector space of finite dimensionality. Every possible finite dimensional representation of a compact Lie group is really the direct sum of irreducible representations. So I look for all the irreducible representations into various vector spaces of different dimensionality. I can produce every representation of any finite dimensionality as the direct sum of these irreducible representations. The bottom line being that if I learn about all of the irreducible representations, right, all of these guys that we talked about, all of these irreducible representations that have no invariant subspaces, if I learn about all of those, I can produce every finite dimensional representation by just taking direct sums of these irreducible representations. And those direct sums will capture every finite dimensional representation as long as the underlying group that I'm dealing with, this guy here, as long as that's compact. Right? This isn't really true for non-compact. And there are plenty of important non-compact Lie groups. So this doesn't completely resolve the issues of total classification. Meaning, total classification means, can I find every representation out there for a Lie group, or can I classify every Lie group by its representations, right? That's sort of what we're after. But for compact groups, we have a fighting chance because we can look for every possible irreducible representation, and from those we could make any finite representation. So at least we can classify things with certain characteristics, namely compact Lie groups and finite dimensional representations. Remember, whenever we say finite dimensional representations, we're saying what we're talking about is these vector spaces here have a certain dimensionality. Remember, a vector space has a dimensionality. It has a bin of scalars, which we sometimes call F. It has its addition operation, right? And this dimensionality, if that is a finite number, then we're talking about a finite dimensional representation, because this general linear group will end up being relatable to n by n matrices, for example. And that's what we mean by a finite dimensional representation. These vector spaces could be infinite dimensional, where we'd need an infinite dimensional representation of G. Okay, next elementary subject. All right, this one is a little trickier. We're going to talk about the tensor products of representations. In order to understand this, you certainly need to understand tensor products, which really are a notion associated with vector spaces. So we can go back to our sketch that we had a moment ago, where we start with a Lie group G, and we have two vector spaces. And I'm going to kind of go back to the old notation I used in my lectures called what is a tensor. I name the vector space V1, name it V2. This is the addition of V1. This is the addition in V2. Notice I'm using the same symbol here. You're just going to have to live with it. I'm not going to write a 1 here and a 2 here for the addition. This is n-dimensional, and this is m-dimensional. And presumably there's a field. Actually, I used to include a field. So there's some field for the vector space, right? Field F. And then in this case, I'm actually going to identify a basis, E sub I and F sub j, because when I understand tensor products, I always think of it in terms of a basis. That's just the way I kind of work. So this has a basis F sub j and a basis E sub I, right? And this group, right, has two representations that are mappings into the general linear group associated with each vector space. Voila. And you'll notice I do not have arrows connecting these things because these guys operate on elements of the vector space, but they don't map into it. These are actual mappings from our Lie group into this group of operators which act on the vector space. Now, as before, I'm going to take these two vector spaces and create another vector space. But where before we created the so-called direct sum vector space, in this case, we're going to create the tensor product vector space. And the tensor product vector space is written as it's written as V1 tensor product V2. Now, often this symbol here, and we will use it later, is also the direct product of groups. But in this case, we're using it as the tensor product of two vector spaces, and that's called V1 tensor product V2. And the tensor product will have its own addition operation, right? It will definitely have its own addition operation. It'll have the same field, right? It'll have its own field. and it will have a basis, and that basis is going to be EI tensor product EJ, and it will have a dimensionality that will equal n times m, right? And this guy is another vector space. And yes, there are mappings from V1 and V2 into that vector space if we want them. Oops. This shouldn't be EIEJ. This should be EIFJ. So the basis vectors of the tensor product space would look like E0 tensor product whoops, I keep doing that. F0, E0 tensor product F1, ... E0 tensor product F, let's see, if it's m dimensional, it's going to be m minus 1, right? And then it's going to be then it's going to be the whole darn thing again, E1 tensor product F0, ... E1 tensor product Fm minus 1, and this will continue to En minus 1 tensor product F0 ... to En minus 1 tensor product Fm minus 1. Phew. And of course, so each one of these is a basis vector of this tensor product space. I'm kind of reviewing what is a tensor, some stuff from the old What is a Tensor lecture.
It's 12 hours.
And what's important about this is, the reason I'm pulling this out is you don't want to think of this tensor product anymore as an operation like E0 operating on F0. Even here, it's not really an operation. It's a combination of V1 and V2, these two vector spaces. And that's exactly what's going on here. This is a combination of two basis vectors, but this thing has to just be understood as another basis vector. And in principle, I could give it a whole separate name. I could call this G sub 0, or maybe even, G is always bad because EF, I could call this, say, H sub 0, and then I could call this H sub 1, H sub 2, and I could go on and on until I have H sub n times m, where that's a number. And I could just relabel everything and make it an n by n dimensional vector space, and that would be completely isomorphic. I'm just renaming everything. So with that in mind, I've created this new tensor product space. And the operations on the tensor product space are pretty straightforward. Meaning each element of this vector space would be expressed as, say, A, I, J, E, I, F, E, I, F, J, right? That would be a typical element. I have to specify it with an I and a J, but that would be a typical element of the tensor product space. And to add two elements together, I just would write it like this, where this is the same field as this, and this EIJ and E, I mean that's another vector, right? You can always add these vectors together. The sum of two basis vectors, by the nature of being a basis vector, is also a vector in the vector space. And also what's kind of important to understand is if you take a vector from V1 and a vector from V2, there is a corresponding vector in the tensor product space. And that corresponding vector would be V tensor product alpha, right? And V would be given by, say, let's see, I guess I would have to do, AIEI, that would be the component breakdown of the vector V in the vector space V1, right? Because we have EI as the basis. So any vector V can be expressed this way. Likewise, the other one would become, how would I write that? Well, I'll just use a different capital letter. B JFJ, right? So I have the tensor product of these two things, and everything is linear in this whole world. So I end up with AI times BJ of EI tensor product FJ, and this is by definition a basis vector in the tensor product space, right? That's one of those things. And then I take this product AI BJ and I usually rename it. I rename it, say, CIJ EI tensor product FJ, right? And so I can talk about the vector space or the vector in the tensor product space that corresponds to sort of the tensor product of two vectors, one from V1 and one from V2. And that is the secret to this notion of representations, right? Because I have a representation to get me from G to the general linear group acting on V1, and I have a representation from G to get me to the general linear group on V2. Now I want to find a representation that will manipulate vectors in the tensor product space of V1 and V2. And so how is that defined? Well, clearly, if I know these two, there should be a way of defining such a third representation that gets me to the tensor product space representation. The idea is that, look, if I have representations of two vector spaces, I should always be able to find a representation of the group on a third vector space that's created from these two. There's only so many ways to create a third vector space from two vector spaces. Direct sum and tensor product are the two that I know off the top of my head. I'm not even sure if there are any others. Okay, but let's have a look at how you make this third tensor product space. Well, it's kind of goes right back to this, right? If I want a representation of the group G that acts on the tensor product of two vectors, V and alpha, right? Well, that is just going to be the tensor product of pi of the first representation acting on V times the tensor product of the second representation of G acting on alpha, right? Because I know that that's another member of V1, so I'll call it W, tensor product, and this is a member of V2, so I'll call it, oh, that W looks a little bit like omega, right? So, because I'm trying to be Roman here. W, that's a vector we'll call W, and this is a vector we'll call beta, and this is just an easily to create member of this space here. So clearly, if I have a tensor product of two vectors, I can transform that tensor product into another tensor product of two vectors, right? This now ends up being a transformation of a tensor product or an element of the tensor product space into another element of the tensor product space. And it's done this way. And that was pretty easy. So that's another very standard way. So this is called the tensor product. Pi is the tensor product representation, right? It's the tensor product representation of the representation pi1 and the representation pi2. And all that means is it acts on the tensor product space of the two vector spaces that are associated with the other representations. It really couldn't be simpler. And also, it couldn't be any otherwise, right? There's no alternative choice here. This is the only way to really do it. So what have we done? We've kind of begun our foray into elementary representation theory. Notice that we really spent our time identifying, hey, what we're interested in are these guys right here. We're interested in these, I better change color, right? Interested in these mappings from some Lie group, which is abstractly defined, into the very concrete or relatively concrete group, the general linear group acting on some vector space, right? And I pointed out that occasionally in books, they just kind of skip it and they just say these group elements are in fact operations. And that you don't lose too much, but we're going to stick with the way Gilmore does it, and a lot of books do, and we're going to actually explicitly talk about these representations, because when we start talking about physics, these guys become the representations themselves become extremely, extremely important. So if we just kind of did this without specifying the representation, we really are losing a lot of the content that we need to focus on. So we're actually not going to go with that method. But before we break for the day, I want to point out that this analysis has been done for the groups. These guys pi are representations of the group, right? Representations of the group. They are not representations of the algebra. Because remember, this Lie group gets associated with a Lie algebra, right? And that Lie algebra has a representation theory also, right? In our next lecture, we'll talk about that. And this is a source of confusion for physicists who study this from the perspective of physics. You may enter this problem through the Lie group method and talk about representations of the Lie group, then all of a sudden find yourself dealing with an algebra and they're talking about representations in a way that's a little bit different. Or you go the other way around and you end up making this weird jump without understanding the full relationship between these things. So we've discussed the representation today of the Lie group, the notion of representation theory of a Lie group. We'll talk about the representation theory of the Lie algebra in our next lesson. Okay, thanks, and we'll talk later.